Welcome everyone to today's Explainer Rock Mechanics 101. Grab a seat, get those notebooks ready. Today we're going to decode the physical properties of the Earth's materials. You know, when most people look at a mountain or a stone building, they just see this massive immovable object. But as engineers and geologists, we know better, don't we? The ground beneath us is actually an incredibly dynamic system of solids, voids, and fluids. Our goal today is to mathematically and conceptually break down exactly what makes a rock tick. All right, here's our syllabus for today's explainer. We'll start with a quick welcome to rock mechanics, then define density and specific gravity. From there, we'll look at porosity, literally understanding empty space, before moving into bulk density and unit weight. Finally, we'll wrap up the lecture with permeability and rock swelling. Let's get right into it. Welcome to rock mechanics. Okay, let's dive into this. We've got a lot of ground to cover today, pun absolutely intended, so let's get our foundational definitions established. Moving into section 2, density and specific gravity. Look, before we can even begin to look at the complex, unpredictable behavior of the ground under our feet, we absolutely must define its most basic, solid properties. Basically, how heavy is it? And how much space does it take up? We'll kick things off with specific gravity. Density, as you likely already know, is just mass per unit volume. Easy enough. But the specific gravity, or the unit mass of a rock, is a comparative metric. It's defined as the mass of the rock compared to the mass of an equal volume of water. Now, why water? Well, because water's density is a perfectly clean 1,000 kilograms per cubic meter. It acts as our universal, super easy-to-use baseline for comparing how heavy rock materials really are. And the neat thing is, the value of the specific gravity ends up being exactly equal to the rock's density when you express it in grams per cubic centimeter. So, how do we actually figure this out in the lab? Notice the classic physical experiment diagram we have here. We take a rock sample and measure it in two very different states. First, we just hang it from a scale in the air. That gives us MD, which stands for the dry mass. Then, we take that exact same sample and dunk it straight into a beaker of water. That gives us MSW, which is the mass suspended in water. And that brings us right to the empirical formula for determining specific gravity. You just take that dry mass, the MD, and divide it by the difference between the dry mass and the mass suspended in water. But hey, there's actually a pretty cool physical story behind this math. To get a truly accurate dry mass, that MD variable sitting on top, you can't just pick a rock up off the ground. No way. You literally have to bake that rock in an oven for 24 hours just to drive out every last drop of hidden moisture. All right, let's build on this and see how it ties into unit weight. While density gives us mass per volume, unit weight brings gravity to the party. By taking the weight, which remember is mass times gravity, and dividing it by volume, we are left with a measurement in newtons per cubic meter. This is an absolutely crucial distinction when you're calculating the actual forces at play in a geotechnical engineering project, like, say, figuring out exactly how much load a foundation can safely support without settling. Section 3, porosity, understanding empty space. Now, let me ask the class a quick Socratic question here. What happens when a rock isn't perfectly solid all the way through? Because I'll tell you right now, in nature, they rarely are. And this brilliantly illustrates the reality of the situation. Check out the diagrams. See those yellow spaces between the brown mineral grains, or the vibrant blue spaces in the rock micrograph on the bottom? That right there is porosity. It is the visual reality that solid ground is actually full of empty voids. When you stand on a rock, you aren't just standing on solid minerals, you are standing on a wildly complex network of microscopic empty space. To calculate this porosity, which we denote with an N, we want to find the exact percentage of open space in a dried out rock. It's simply the volume of those open spaces divided by the total volume of the rock times 100. In a lab setting, engineers calculate this percentage by taking the mass of the saturated rock in air, subtracting the dry mass, and then dividing all of that by the mass of the saturated rock in air minus the mass of the rock suspended in water. Basically, it tells us exactly how much fluid a seemingly solid object can actually hold. Now, not all empty spaces are created equal. We generally classify these into two main types. Primary voids exist naturally right between the fragments of sedimentary rocks, and they tend to be highly consistent. Secondary voids, on the other hand, are caused by things like fracturing or weathering over time, and these are highly variable, completely unpredictable. If you're ever working with dolomite or limestone, secondary voids are incredibly important to watch out for because water can carve out massive, unpredictable channels through them over time, leading to catastrophic sinkholes. What's really wild about this slide, though, is the sheer scale of these voids, depending on what material you're looking at. Metamorphic rocks are incredibly dense. They boast a porosity of less than 5%. Sandstone sits around 10 to 15%. But look at clay or standard soil, up to 50% porosity. It's a bit of a shock, isn't it? Half of the solid ground beneath your feet right now might actually just be completely empty space. And that is exactly why building on clay is so notoriously tricky. You're practically building on half air and water. Moving into Section 4, bulk density and unit weight. Now that we understand both the solid mineral grains and the empty voids, we've got to combine them into one cohesive mathematical picture. Because rocks are porous, the specific gravity of the rock as a whole is always going to be lower than the specific gravity of just the individual mineral grains themselves. Look at the math we have here. The bulk volume is the volume of the grains plus the volume of the pores. So the bulk density incorporates both the grain density and the pore density. But here is the kicker. If those pores are just filled with air, the pore density is practically zero. In that case, the formula simplifies beautifully down to just 1 minus the porosity times the grain density. But what happens when those pores aren't just filled with air? The pores of rocks in the earth can easily fill up with water. And since a dry, porous rock's weight is directly related to its density, adding water into the mix fundamentally changes the math. A saturated sample is always going to be heavier than a dry one. Water finding its way into those voids totally changes the weight, the density, and the structural behavior of whatever earth material you're analyzing. This is a massive factor in predicting phenomena like landslides right after heavy rains. Section 5, permeability and rock swelling. Okay, so we know the rock has voids, and we know fluids can fill them. Now let's talk about how fluids actively move through and physically alter these materials. Permeability is simply the ability of a fluid to pass through a rock, and it relies on a few really key factors. First, the interconnectedness and size of the voids. If the empty spaces don't touch, the water can't travel, right? Second is the viscosity of the fluid itself. And third is the hydraulic gradient. Gravity is always going to pull that fluid from a position of high hydraulic pressure down to one of lower hydraulic pressure. So the crucial point is how we actually calculate that movement. Enter Darcy's law. V equals K times I. The flow rate, V, is simply the rock's permeability coefficient, K, multiplied by the hydraulic gradient, I. This elegant little equation mathematically summarizes everything we just learned about how fast water will travel through ground material. It's the essential math used to model groundwater flow or to predict exactly how underground pollution might spread. But remember, water doesn't just passively flow through a rock, it interacts with it. When soaked in water, earth materials will basically react in one of three ways. First, you have rigid rocks, which stay perfectly structurally sound. They don't swell at all. Then you have flexible rocks, which absorb the water and physically swell up. And finally, you have disintegrating rocks, which literally just fall apart when introduced to fluid. For those flexible rocks, engineers have to measure exactly how much they change. We use the swelling coefficient, which we denote as ES. It is a really straightforward measurement. You take the length of the dry rock, LD, and divide it by the length of the saturated rock, LW. This tells us exactly how much a material's physical dimensions will expand when introduced to an underground water source. And let me tell you, it's absolutely vital for tunneling and foundation work, because a swelling rock can literally heave and crack solid concrete. Which leaves us with this final thought for today's lecture. We started off by looking at rocks as these heavy, immovable, solid objects. But through the math, we've proven that the earth beneath us is actually filled with massive empty voids, moving fluids, expanding materials, and hidden fractures. So I leave you with this question. If all of that is true, is solid ground just an illusion? Think about that the next time you step outside. Class dismissed.